Well, good morning, everyone. At least it's the morning while I'm filming this, and you might be able to tell, feeling a little bit cold today. Um, we're going to be looking at the first four questions on your practice test here for Chapter 4 in AP Statistics. This is experimental design. So let's head on over to the content here, and we'll take a look at what we have. So you're going to design a research project on the attitudes toward fast food and decide to use as your sample the first 25 people to enter the door at a local fat burger restaurant. What type of sample does this best describe? Well, the one thing that kind of gives this away is that you're not really doing a whole lot of work to create the sample. You're just kind of going along and picking whatever 25 people you find at a single establishment. So that really does tell us that this is a convenient sample. This is a bad sampling technique. If you're going to make a good sampling technique, you would have to make sure that you've made an effort to do some randomization. Make sure that you have a sample that doesn't underrepresent the population. And this does neither of that. This sample only really is a sample of the first few people who enter a single fat burger restaurant. You might make the argument that this sample would represent everyone who goes to that fat burger restaurant during the day, that particular fat burger, but then that's a really bad argument because you're only taking a sample at a specific time of the day. The other thing you might say is that this sample is a sample of fat burger restaurants, and again, it does a bad job of that because there's only one fat burger restaurant at one time of the day. So it doesn't make a real, a good convincing sample of anything other than not even the fat burger restaurant. This is just a bad sample. I have no way of justifying this. Number 2, how does an experiment differ from a observational study? Well, firstly, an experiment makes an attempt at control by assigning treatments to the different experimental units, and it also makes an attempt at control. That's the experimental design control, by carefully selecting its experimental units. Remember that the reason that we do this is, the assigning treatments allows us to better assign or to better analyze to see if there's a cause and effect relationship between the treatment and the response. Carefully selecting experimental units is done as literally control for the experimental design sense of control, because you are trying to screen out any of the confounding variables that might come in just from allowing any experimental unit to enter the experiment. So, for example, if we're going back to testing aspirin for blood pressure, then you want to make sure that when you screen, anybody who's coming into your experiment does not have some other factor that is affecting blood pressure. That's an instance of control. This is different than an observational study because an observational study is just a survey. It doesn't assign treatment to the experimental units. So it just looks at what's already happened and categorizes based on the experimental units and perceived treatments and perceived responses. Observational study, at best it'll make a minimal attempt at control by, choosing the experimental units to include in the observational study. So it's a very marked difference really between the two. And usually the biggest tell is this idea about assigning treatments to the experimental units. If you assign treatments, that's an experiment. If you don't assign treatments, then that's an observational study. Okay, let's take a look at number 3. You want to do a survey of members of senior class at your school. You want to include 40 students in your sample. So classify each of the following sampling methods. Does this method produce a simple random sample? And that's a little bit of a weird question, because only a simple random sample is truly a simple random sample. But let's go along with this anyways. So letter A, write the name of each student on senior class on a slip of paper. Put all the papers in a container. Then randomly select 40 slips of paper from the container. Okay, this is a simple random sample, and it's a classic example of a simple random sample, really. And the thing I would like to say is, if you ever get stuck and you don't know how to create a simple random sample, writing names on papers and pulling them out of a hat is always going to be a simple random sample. And let's go over this. It's a simple random sample. Every subset of n subjects has the same probability of selection, of being selected. And this happens because there's no mechanism that's preventing you from choosing any two different subjects together, or any set of n subjects together. So classic simple random sample. Number 2, assuming that the classes are not tracked, select 2 classrooms at random and include those students in your sample. Okay, this is a cluster sample, and this has the classes themselves as a sample. Now, you can kind of tell that this is a cluster sample because when you're choosing your students, you're choosing the entire classroom to be included in the sample. And that's really different from all of the other sampling techniques. If the subjects are the students and we're picking a whole group of students at a time, then that is indicative of a cluster sample. So the group of students are being chosen randomly. The group is being chosen randomly, not the individual student. Okay? And because we're selecting an entire group, then this is not an SRS. And to add detail of that, this is not an SRS because students in different classes, or if we have class A and class B, the probability of 2 students being selected in different classes is slightly different than the probability of 2 students in the same class being selected. That brings us to letter C. From a list of seniors, select the one of the first 10 names at random, and then proceed with every nth name on the list until you have 40 people selected. So this is a systematic sample. There is a mechanism for selecting the students, a mechanism that has to do with, every so many names until the sample size has been filled. This is a pretty classic example. And I like to think that the reason why we would not call this a simple random sample is because 2 names that are right next to each other on the list, they have a low probability of being selected together. You can see this a lot. The sample is used a lot during random backpack searches and things like that. It's not an SRS, and that doesn't mean it's a bad sampling technique. Every student has the same probability of being selected, but it's just not an SRS. And right, it doesn't mean it's going to produce a bad sample. It's just going to mean that it's not... every subset of students doesn't have the same probability of selection. So, oftentimes in AP Stats especially, students like to think of the SRS, or they come to think of the SRS as like a gold standard for randomization. And it's not a gold standard of randomization. It's just the SRS is only a type of sample that we know a lot about and we can do some interesting statistics with. So we tend to favor it. Letter D, select the first 40 seniors that passed through the cafeteria door at lunch. So this is very simple or very similar to that fat burger example from earlier. This is a convenient sample. There are minimal attempts at randomization and minimal attempts also at population representation. So we're only selecting from one place at one time, and we're not even really doing a whole lot of randomization. We're just saying the first 40 students. So yeah, those first 40 students probably represent a random sample because who knows who's going to come in, but it's not truly representative of the entire population. So for those two reasons, this is not an SRS. And letter E, randomly select 10 students from each of the 4 senior calculus classes. And this is a stratified sample. But, I tell you, this is not a great stratified sample. So in this instance, the strata are the calculus classes and the individuals are the students. So when you think about it, this sample is only really going to represent calculus students. Of course, if you're only meaning to sample from calculus students, then this is probably going to be okay for you. But if you were meaning to sample the entire student body, then this is not going to do a great job because students in calculus probably have different opinions than the rest of the high school. So stratified sample, we also said that this was not an SRS because it's impossible to have a sample here where all students are from the same calculus class. In our SRS, that has a low probability of occurring, but it still has some probability of occurring. Whereas with a stratified sample, that has no probability of occurring because you're spreading out to the individuals in the sample among all the different strata. So that is our stratified random sample. These are 4 of the, I think we had, let's see, I think we had 7 different sampling techniques that we have identified in this class. Some good, some bad. The ones that we didn't talk about here is that voluntary response sample where students or experimental units self-select themselves to be part of the sample. And the last one we're going to do here for this morning is what are the 4 principles of experimental design, and give an example of each. Firstly, we have comparison, and by comparison means we have to compare values of a measurable response variable from multiple groups. We can't just say, hey, this one looks better than this one. We've got to make sure we have something measurable, a number to report, something to report from those multiple groups. So one example of this that we can see is, let's say that we are measuring the average acidity level of 2 samples of treatment groups. So in this case, again, we're doing some sort of comparison. We're comparing average acidity levels, and it's important that we have 2 groups to compare so we can see, is there an effect on the average acidity level, assuming, of course, that the average acidity level is our response variable. Next, we have random assignment, and that's going to be a chance process that assigns treatments to different treatments to different groups. Now, the reason we want to do that is because we want to distribute confounding variables amongst the different groups. Now, the confounding variable is always going to exist, or always going to be things that we don't know about in our subjects or experimental units. They're going to exist different things among the individuals that will affect their response. So because we can't control those confounding variables, we're just going to have to try to distribute them in an even manner. And the best way to do that is with a random assignment. We don't know what they are, so we'll randomly put them in different groups and hope that they are distributed equally. Some example of this would be just take the first 4 names drawn from a hat, and they're going to put them in group 1. The remaining 4 are going to go to group 2. Next, we have control. So we want to keep all the variables other than the treatments constant, or at least as constant as possible. This could be summarized really with don't introduce new confounding variables. And what this looks like is a pre-screen of the subjects or the experimental units to make sure that they are alike in as many ways as possible. This means that the probability of confounding variables amongst them are going to be hopefully lower than if you just had a bunch, a really motley crew of experimental units. So one example of this, which is probably not a great example because it is a little bit charged, but if you only use rabbits from the same breed line in a laboratory, then you're sure that the rabbit's individuality due to breed is not going to be a confounding variable. So this is something that you're going to see often in especially experiments involving animals. And I know this is not a great example and I don't recommend it, but using, the same breed line or the same kind of animal would be an instance of control. So the next one, and the final one here, is replication. So this means in your single experiment, you want to use many experimental units. And the reason you want to do that is because you are already aware that there are confounding variables that are going to exist no matter what you do. So because those are out there, your only hope, or not your only hope, but one of your best hopes to mitigate the effects of those are to use many experimental units. So when you compare an average, then those confounding variables are going to tend to average out. If there is an outlier due to a confounding variable, then the process of taking an average with a lot of experimental units is going to bring the effects of that one outlier down. So that's the reason why we do replication. It's because we're going to try to average the effects of the confounding variable, if they exist, and get something that is truer, hopefully, to the effects of just our explanatory variable. So that's it for us on this, our practice test example. Hopefully that works for you, and I'm going to see you guys later. Don't forget to study, and we'll see you next time here on AP Stats. See you later, guys.